Hello, everybody. Welcome to the Exam 2 review video. Just a quick disclaimer, this is a guide to help you study. It's not the end-all be-all or the holy grail of reviews. Make sure you use your workbooks to kind of help you with some of the gaps that you might have and study the exam review packet. That is the best way to study, and it will help you the most for the exam, as you probably know from last exam. So let's get right into it. Chapter 4 was about exponential functions and logarithms. So we had this percent change in times as large as notation. I want you to go ahead, pause the video, and try to do this yourself. A shirt is on sale for 17% off. What's the percent change? What percent of the original price is the sale price? And how many times as large is the sale price compared to the original price? So I'm assuming you've paused and tried it on your own. The percent change is going to be negative 17%, right? The shirt's price is going to decrease, so it's going to be negative, and it decreased by 17%, so negative 17%. Well, percent change is just how much, is just what we changed from 100%, right? So our new percent is just 100% minus 17%, or 83% of the original price, right? If our shirt was originally $100, well, now it's going to be $17 off. It's going to be $83, which is 83% of that original price. How many times as large is the sale price compared to the original price? Well, if it's 83% of, it's 0.83 times as large as. Moving on to exponential functions. These were functions whose ratios between outputs for equal sized changes in inputs was constant. So for example, if we had f of 2 divided by f of 1 equal to f of 3.2 divided by f of 2.2, which was equal to f of 10 divided by f of 9. And so for any 1 to 2, that's a change in 1. 2.2 to 3.2, that's a change in 1. 9 to 10, that's a change in 1. For any one size change in our inputs, if all of these ratios are the same, we have an exponential function. And so this ratio right here would be our 1 unit growth factor, our f of x plus 1 divided by our f of x. Our ratios between outputs who are 1 away. Whose inputs are 1 away, excuse me. The general formula that we use is f of x is equal to c, our initial value, so that would be f of 0, times our 1 unit growth factor to the power of x. Okay? So we didn't just have 1 unit growth factors, though. We also had n unit growth factors. So for example, we would also have that any of these ratios right here are identical and equal to the 3 unit growth factor. So our 1 unit growth factor was when we had inputs that were 1 away. Our 3 unit growth factor was when we had inputs that were 3 units away. And our n unit growth factor is going to be just when we have n units of distance. That can be general. But our formula in this case is going to look like our initial value, so that doesn't change. And by initial value, I always mean f of 0, what our function is at when our input is 0, times our n unit growth factor and let's think of this. How many times do we apply our 1 unit growth factor in n units? N times, right? So what we're actually going to do here is we know that our 1 unit growth factor is just the nth root of our n unit growth factor, right? So for example, our 3 unit growth factor is the 1 unit growth factor applied 3 times. So it's the 1 unit growth factor cubed. So going the other way, we know our 1 unit growth factor will be the cube root of our 3 unit growth factor. Because we have to apply our 1 unit growth factor that many times within n units, we're going to raise this to the power of x divided by n, right? So we're saying that every n units, we're going to apply this n unit growth factor. And we know that our 1 unit growth factor is just our n unit growth factor to the power of 1 over n, which is the nth root. So as an example, this is number 10 from your exam review. This is just one that I picked. Please pick more, because there are some really good problems on there. But we're going to suppose that h is an exponential function, so that h of 3 equals h of negative 3 equals 4, and that the 3 unit growth factor of h is 2.5. what is the value of h of 0? What is the value of h of 3? What is the value of the 1 unit growth factor? And define the function h. So pause and try that on your own, but I'll start now. H of 0, well, let's just take a look at h of 3. We know that h of 3, or excuse me, h of negative 3 is 4. And we know that our 3-unit growth factor tells us what we need to multiply something by to get the value of the output 3 units later. Well, what's 3 units later than negative 3? 0. So h of 0 is just going to be h of negative 3 times our 3-unit growth factor. It moves us forward by 3 units in our input. And so we get 4 times 2.5, which is 10. We can use that same logic to find h of 3. Well, that's going to be h of 0 times our 3-unit growth factor, or 10 times 2.5, which is 25. Now for part C, what is our 1-unit growth factor? And I want you to think, here's our 3-unit growth factor right here. To get our outputs over an input change of 3 units, we multiply by our 3-unit growth factor. How many times would we have to multiply by our 1-unit growth factor in this time period? We'd have to multiply it 3 times, right? So from, let's say, 0 to 1, 1 to 2, and 2 to 3, we'd have to multiply by our 3-unit growth factor to get from 0 to 3, but we'd have to multiply our 1-unit growth factor 3 times to get that same thing. So our 1-unit growth factor cubed is equal to our 3-unit growth factor, right? Moving forward by 3 units is the same as moving forward by 1 unit 3 times. And so solving, we get that our 1-unit growth factor is the cube root of our 3-unit growth factor, which was 2.5. And we put that in our calculators, and we're going to get 1.357. Around there, rounding, of course. So it's right 1.3572, and then some change. Finally, part D, we're going to define the function h. Well, I know my initial value is going to be h of 0, which was 10. So I have 10. And the way that I want you guys to think about this is using what we were given. So our 3-unit growth factor was a lot nicer to work with. So let's do 2.5. And I know that this is going to be applied every 3 units. So I'm going to put it to the power of x divided by 3. And this is our final answer. It's saying that we start at h of 0 equals 10. And to move forward by 3 units, we multiply by 2.5. So question 30 is another good one. I'll let you do parts C through E on your own. But again, try to do this whole exam review packet. It is really the best thing to do to study. We want to know that an environmental scientist is studying the concentration of bacteria in a lake as measured in parts per million. She obtains measurements of concentration on the first day of the month for several successive months, and she shows us a portion of her data here. If she assumes the concentration is growing exponentially, what concentration should she predict for the first month, or for the first day in month 5? Well, let's find our 2-unit growth factor. To go from 60 to 93.75, we're going to have to multiply by 93.75 divided by 60, right? This is our 2-unit growth factor, because it's our output for month 3 divided by our output for month 1. Those 2 different inputs, months, had a difference of 2. And so this is our 2-unit growth factor, the ratio between those 2 outputs. You put that in your calculators, and you are going to get 93.75 divided by 60, 1.5625. Okay. Now, we want to know what the concentration you should expect in month 5 is. And we know that our 2-unit growth factor is 1.5625. And that's what we multiply 60 by to get 93.75, right? It moves us forward 2 months. So to move us forward another 2 months, we just multiply again. So times 1.5625. And we're going to try that out. So 1.5625 times 93.75, we're going to get, excuse me, 146.48 parts per million. So 146.48 ppm. Now we want to find what bacterial concentration she should predict for the first day in month 2. Again, pause, try on your own. How do we get our 1 unit growth factor from our 2 unit growth factor? Well, if I draw here, I know that my 1 unit growth factor, if I multiply once, will take me from 1 to 2. And if I multiply again, will take me from 2 to 3. So our 1 unit growth factor squared has to equal our 2 unit growth factor, that 1.5625. So our 1 unit growth factor is just the square root of 1.5625. And if you put that in your calculators, you should get 1.25. So then, to get from day 1 to day 2, let's multiply 60 by 1.25, and we're going to get 75. So 75, parts per million. Moving on to logs and solving exponential functions, we know that the equation b to the x equals m is equivalent to saying that x is log base b of m. So logarithms are the ways that we can switch between our exponential form and solving for what's in that exponent there. So again, when we say that 2 cubed equals 8, that's the same as saying that the log base 2 of 8 equals 3. Log base 2 of 8 is saying, what do I need to raise 2 by? To get 8. And our answer is 3. 10 to the power of x equals 340. Well, we're using that same thing here. Our base is going to be 10. So log base 10 of 340 equals x. I'm saying, what do I need to raise 10 by to get 340? And our answer was x, right? 10 to the x equals 340. And finally, log base 9 of x equals 12. Well, that's saying, what do I need to multiply, or excuse me, what do I need to raise 9 by to get x? And it's telling me that the answer is 12, which is the same as saying not x equals 9 to the power of 12. So again, logarithms and exponents are inverses of each other, which means if I have 2 to the 10 plus 4x equals, let's say, 7, then if I want to get rid of this 2 to the power of to solve for x, I'll take log base 2 of both sides. So log base 2 of all this equals log base 2 of 7. And log base 2 and 2 to the power of cancel out. So I'll get 10 plus 4x is equal to log base 2 of 7, which you could then solve. Oop, you did not see this. Go ahead and try these on your own. We're going to try to convert between log form and exponential form for the following expressions. Our first one is log base 5 of 125 equals x. So this is saying, what power do I need to raise 5 by to get 125? And I'm saying that the answer is x. So 125 is equal to 5 to the x. This bottom one down here, we have 2 to the x equals 64. I'm saying, what power do I need to raise 2 by to get 64? The answer is x. Our third one down here, log base 2 of x equals 3. I can raise 2 to the power of each side to get x equals 2 to the negative 3. Because this first thing is here is saying, what power do I need to raise 2 by to get x? The answer is 3. In other words, 2 to the power of negative 3 is x. Finally, we have 3 to the negative 4 equals x. To use my log form here, I'm saying, what do I need to raise 3 to the power of to get x? The answer is -4. So a little example, number 32, the population of insects is growing according to this equation right here, where t represents the number of months since the experiment began. I want you to try part G on your own. Which of the following expressions represents the number of months needed for the population to grow to 9,000 insects? Okay, assuming you've tried that now on your own. Our population is A of t, right? So we need to know when A of t equals 9,000. But A of t is equal to 5,000, excuse me, is equal to 5,000 times 1.2 to the power of t. We want to solve now for t. So let me divide both sides by 5,000. I'm going to get 9,000 divided by 5,000 equals 1.2 to the power of t. I'm asking, what power do I need to raise 1.2 to get 9,000 over 5,000? That's this question right here. Looking at all our responses, this is the only one that works, because this one takes the log of both sides and then divides by 5,000. I'm not quite sure what this one is doing, or what this one is doing. A lot of these don't make too much sense, right? So as long as you're able to solve for t and get it in an exponential form, so 9,000 divided by 5,000 is equal to 1.2t. Well, we can take log base 1.2 of both sides to get t on the right, and log base 1.2 of 9,000 divided by 5,000. All right, moving on to chapter 5. This was on polynomials and power functions. So we started off with the bottle problem, and I'm going to use 28 as an example. So we're given this graph on the right that represents the height of water in inches in a bottle as a function of the volume of water in milliliters in a bottle for which of the following? It's asking us which bottle fits here. Pause, think about it yourself. All right, so I'm going to break this up into a bunch of pieces that represent equal lengths of volume, right? This is like me adding that 1 cup over and over and over again, right? Well, at first, adding 1 cup makes our height increase a lot, right? But as we keep adding that cup, it starts having less and less of an effect. And so I know that it has to be getting wider here, right? Until a point, and then it starts to have larger and larger changes. It starts to get more and more effective. Putting that same cup in, it'll have a more and more drastic effect on our cup size. So it then gets skinnier. And the only bottle that gets wider and then skinnier here is E. So concavity. Concave up meant that our average rate of change over some interval was increasing. So we had 2 options for that. We could have that our average rate of change, the slope of these lines, was increasing at an increasing rate, right? Our function here is increasing. It's going up as we go to the right. And it's increasing at an increasing rate, right? These are getting steeper and steeper and steeper. It could also be decreasing at a decreasing rate. So even though it's decreasing, this is still concave up because that average rate of change is increasing, right? Even though it's decreasing, the average rate of change is negative. It's getting less steep. So it's going towards positive, right? And if we put both of these together, we could start off decreasing at a decreasing rate until eventually we started increasing at an increasing rate. And this would all be concave up. Concave down was the opposite. It's when our average rate of change was decreasing. We could have decreasing at an increasing rate, right? Our function is decreasing, and it's decreasing at a faster and faster rate as we keep going along. So these lines are getting steeper and steeper and steeper, still decreasing. Or we could have increasing, right? So our graph is going up, but at a decreasing rate. So it's starting to curve towards decreasing. So putting those together, we could have increasing at a decreasing rate until it starts decreasing. This is concave down. quick recap on function transformations. Remember, our vertical shift is when we add something to the outside. We're affecting our outputs here, right? So this is our output. We're adding something to it. It's going to shift it up by k units. If k was negative, it would shift it down. A vertical shift is, again, affecting our outputs, our f of x. That's when we multiply the outside of our function by some constant. And it's going to stretch or squash, depending on what k is, our function. Horizontal shifts, or what happens when we do something to our inputs. We're shifting our inputs here, so we're changing x. So this is saying that the output for if j of x was equal to f of x minus k, so this is our f function right here, this black function. Well, then the output of j of x is going to be the same as the output of f of x, k units before. And so we have to shift f of x, k units to the right to make that happen. So again, f of x minus 2 is to the right by 2. And f of x plus 2 is to the left by 2. Be careful there. A vertical reflection is, again, what happens when we're doing it to our outputs. We're multiplying our outputs by a negative sign, which has the effect of just flipping our outputs over, right? So for the same inputs, we're going to have the same magnitude of outputs, but just in the opposite direction. Our horizontal reflection is a reflection, but on our inputs. So what we're going to do is we're going to have the same outputs, but just for inputs that are on the other side, right? So blue, blue, blue. So moving on to end behavior of polynomials. Remember, we need to take the leading term, so the term with the highest power in it, and ask ourselves what's happening when x gets really, really large and when x gets really, really negative. So x goes to infinity or minus infinity. So first of all, consider this function, g of x equals 4x to the 5th minus 7x to the 4th plus 10x cubed minus x plus 3. What monomial function best approximates the end behavior of g of x? And which of the following functions have the same end behavior as g of x? So there are multiple here. So have. Again, go ahead and pause, try that on your own, but I'm going to start now. Let's find the leading term in g. We have x to the 5th, x to the 4th, x cubed, x, and x to the 0. So our highest order term is this 4x to the 5th. And so that's the monomial function that best approximates our end behavior, 4x to the 5th. And let's test some values. So as x goes to infinity, 4x to the 5th, well, let's think about 4 times 10 to the 5th. That's going to get really big and positive. 4 times 100 to the 5th, that's also going to be really big and positive. This goes to positive infinity. But as x goes to negative infinity, this is 4 times a negative number, so negative 10, for example, 5 times. When we multiply a negative number by itself an odd number of times, that's going to still be negative. So this is going to be a really big negative number. That goes to negative infinity. So for part B, we want to look at functions that are going to infinity as x goes to infinity, and negative infinity as x goes to negative infinity. So for h of x, let's find our leading term, 4x to the 6th. You can use that same logic here to show that the end behavior, as x goes to negative infinity, h of x will go to positive infinity because it's an even multiple. For k of x, we have 3x to the 7, and you can check that this works. So k of x works. 3x to the 7, we have an odd power here and a positive coefficient. For m of x, we have negative 4x to the 5th as our leading term. But if x goes to positive infinity, negative 4x to the 5th goes to negative infinity, right? Since we're multiplying 4x to the 5th by negative number, that goes to negative infinity. So it's not m of x, it's not h of x. Let's look at p of x. 1/2 x cubed is our leading term. And again, we have a positive coefficient out here and an odd power. So yes, this works. So our answers are k of x and p of x. Next problem is a really solid problem that I recommend we do on our own, but we're just going to look at multiplicities for a second. We want to know what the roots of f are and their multiplicities. So pause and find the roots of f. And for their multiplicities, I want to know whether they're even or odd. I'm going to start. Remember, our roots of f are our x values where the function is 0. So x equals -50, x equals -10, x equals 25, and x equals 35 are our roots. Now remember, if a root, so let's look at the graphs of x and x squared here. X and x squared both have a root at 0, right? But x squared kind of bounces off while x goes through. Anytime a root has the graph go through, so it changes from positive to negative, our root has an odd multiplicity. So let's label those. Odd, because it goes through, odd, because it goes through, and odd, because it goes through. But whenever we have an even multiplicity, it's going to bounce off the x-axis. So it's going to hit it and then turn the other way. It's going to stay all negative or stay all positive, like this one right here. So x equals -10 has an even multiplicity. Please try to do this whole thing. It'll help you immensely for the exam. Moving on to quadratic functions, the big things that we had were our two forms. We could have it in standard form, our ax squared plus bx plus c, or we could have it in factored form. So our a, x minus our first 0 times x minus our second 0. When our leading coefficient is positive, a is greater than 0, our graph is happy, it's facing up. And when our leading coefficient is negative, it's concave down everywhere, it's frowning. The most important part of a quadratic function, and I'm circling this a billion times so that you know, is that vertex. That is where our maximum or minimum value is going to occur and where the function has symmetry. So ignoring that I drew mine a little bit wonky, all of these graphs have symmetry about the line -b/2a, which is their vertex, or excuse me, their line of symmetry, or the x-coordinate of their vertex. So remember this very well for your standard equations. If anytime you see maximum or minimum and you see a quadratic function, you're going to use this. If we had it in factored form, finding our vertex is a little bit different, but still the same. We know that the vertex has to lie halfway between these two zeros because we have that symmetry. So just take your two zeros, add them up, and divide by 2 to find their midpoint. Remember that the vertex is an ordered pair, so you need both the x and the y. So the -b/2a and the f, the function's value at that point. Again, anytime you want the minimum or maximum of a quadratic function, find the vertex. Memorize -b/2a. And remember x1 plus x2 over 2. So the quadratic formula, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. If you've heard that song, you should have. It's like mandatory reading, basically. This gives us our roots. It gives us where our x values where the function equals 0. And it's telling us, right, that here's our line of symmetry. Our x equals -b/2a. Plus or minus this square root of blah, blah, blah. This is the distance from our vertex. Or excuse me, the distance from our line of symmetry. I really, really, really recommend that you do problem 26 for this. It's one of the only exam review problems that goes into it, and it'll be really important for helping you study for the exam. All right, moving on to our last chapter for this exam was rational functions, starting off with end behavior and horizontal asymptotes. So remember, f of x is going to be some numerator polynomial divided by some denominator polynomial. As x tends to plus or minus infinity, remember from before that our polynomials just look like they're leading terms. So an example, f of x equals x plus 3 divided by x cubed plus 1, as x goes to plus or minus infinity, is what this should say, f of x is just going to look like the ratio between those two leading terms. So our leading term for the top is x. Our leading term for the bottom is x cubed. And this looks like 1 over x squared. And let's think about what happens to 1 over x squared as x gets really big or really small. So x tends to plus or minus infinity. Well, this is fractions, right? 1/10, 1/100th, 1/1000th, 1/1,000,000th. If you take their decimal values, what does it look like that's getting really close to? It's getting really close to 0. So f of x will tend to 0, and it will have a horizontal asymptote at y equals 0. Whenever f of x tends to a constant value, k, as x tends to plus or minus infinity, we say that f has a horizontal asymptote, y equals k. You were given a really good way to figure out horizontal asymptotes and when it doesn't have a horizontal asymptote in your 6.1 lesson. Go revisit that in your workbook. Super helpful. But remember, if the power in your numerator was larger, so for example, x cubed plus 2x plus 4 divided by x squared minus 1, well, as x tends to infinity, f of x is going to look like our leading terms, our ratios of our leading terms. So it looks like x cubed over x squared. But that looks like x. And as x goes to plus or minus infinity, f of x will also tend to plus or minus infinity. So there is no horizontal asymptote. If we had it flipped around, so x squared minus 1 over x cubed plus 2x plus 4, well, then f of x will tend to that ratio of our leading terms, x squared over x cubed. But simplifying, we get 1 over x. As x goes to infinity there, f of x will tend to 0. So there's a horizontal asymptote at y equals 0. Excuse me. Finally, when both powers were equal in the top and the bottom of our leading terms, let's say, for example, 3x squared plus 2x minus 1 divided by 4x squared plus 2 plus 3x. Our leading terms here, as x goes to plus or minus infinity, f of x is just going to look like 3x squared over 4x squared. But simplifying, we get 3/4. That's a constant. So we have a horizontal asymptote at y equals 3/4. Okay. Graphically, horizontal asymptotes are going to be y equals k. So they're going to be a horizontal line. And our function is going to get closer and closer to that line as we go to plus and minus infinity. So as we go to the right, or we move all the way to the left, our function is approaching that line. Vertical asymptotes. Remember in math that dividing by 0 is undefined, and that weird things start to happen when the denominator is 0. So I'm going to do question 21 with you guys. We're considering this function f of x equals x minus 2 divided by x plus 3. Part A, what is the domain of this function? Again, I want you to try this yourself, but I'm going to start it now. Come back to me once you're finished. But part A asks us, what is the domain of this function? Well, we know that we can never divide by 0, so x cannot equal -3. And so drawing a number line here to help us, I'm going to know that there's a hole at -3. And so my domain is going to be everything past -3 and everything before -3. So -infinity to -3, not included, union with -3 to infinity. Part B asks us for a vertical intercept. And I want you to think back to what that is. It's not asking for a vertical asymptote. What was our vertical intercept? Our vertical intercept is the point 0, comma f of 0. If you were to graph it, it would be whatever's on the y-axis right here. So let's test that out. F of 0 is 0 minus 2 divided by 0 plus 3, so it's -2/3. Part C is asking us for the zeros of the function f, or the roots. Well, The roots are going to be when the numerator is 0. So x equals 2. Part D asks us for the horizontal asymptotes. Whenever you see horizontal asymptotes, you're going to need to use that end behavior. So we're going to say as x tends to plus or minus infinity, f of x is going to look like our leading terms. So x divided by x, which is equal to 1. So as x tends to plus or minus infinity, our function tends close and close to 1. That means that we have a horizontal asymptote at y equals 1. Part E asks us where our vertical asymptotes are. And again, vertical asymptotes are where our function is undefined and we can't do anything about it. So it's where x, our denominator, is 0, or where x equals -3. Okay. Finally, we want to compute our limit as x approaches infinity of f of x. But we just did that here. We had our horizontal asymptotes. That's what I used to calculate our horizontal asymptotes. I know that this is 1. Same as the limit as x goes to negative infinity, right? As x goes to negative infinity or plus infinity, our f of x is just going to look like that ratio between our leading terms, which is just 1. Finally, we want to sketch a graph of this function, which I'm going to do so here. What I recommend for this is literally plot everything that it asks you for. The domain of the function is everywhere except for -3. So I'm going to put -3 down here. I know I have a 0 at 2. So I know there's going to be a point here. My vertical intercept was 0, comma -2/3. So let's just say this is this is -2/3 right here. And I know that I had a horizontal asymptote at y equals 1. So I'm going to draw a line like this. So I know that my vertical asymptote is at x equals -3, and I need to draw a function that's contained in here, which is going to look something like this. It'll let me. And you can check using Desmos. But again, we have our vertical asymptote right here. We have our root right here. Oop. I did not do a good job of that. Give me just a sec. This is -2/3, right? We have our vertical intercept right here. And that our horizontal asymptote is y equals y equals 1. So as I go all the way to the right, or as I go all the way to the left, my function is approaching 1. My function value is approaching 1. All right. Last thing to study was that limit notation in rational functions. So once again, whenever we have a rational function, we're going to have a numerator divided by a denominator. The value of f of x is telling us how many times as large as the denominator is the numerator. So f of x, if f of 1 equals 12, that's the same as saying that when x equals 1, the numerator is 12 times as large as the denominator. Please study that for your exam. But let's go through question 33 together, and then we're done. So again, please try your best to go through that whole exam review. That'll be what is going to help you most for the exam. But yeah, without further ado, this following picture shows the graph of a rational function with a vertical asymptote at x equals -3. Let's label that. And a horizontal asymptote at y equals 1, and which passes through the point -4, 6. Which of the following statements is true? Try it yourself. Okay. The point -4, 6 on the graph of this function, let's look at part A, indicates that this location, the value of the numerator is -4, and the value of the denominator is 6. Is that true? No, that's not true, right? 1, this has nothing to do with numerator, and this has nothing to do with denominator. This is our input. This is the ratio between our numerator and our denominator, right? So you could also say that, okay, well, if that was true, let's say the numerator was -4 and the denominator was 6. We should get back 6 because this is f of -4, right? So it's not A. For question B, the point -4, 6 on the graph of this function indicates that at this location, the value of the numerator is 6 and the value of the denominator is -4. Again, this doesn't really make sense. So that leaves us with part C. When x equals -4, the value of the numerator is 6 times as large as the value of the denominator. We know that this means f of -4 equals 6, and that's exactly what that's saying. So our answer is C. I hope this has been helpful, and good luck on your exams. Again, make sure you please do that whole review packet. It is the best thing that you can do. Bye-bye.